Hey, I'm here to talk about conservation of current. It's kind of similar to conservation of charge because current is just charge per time. And basically says, like, if you've got current that goes into a junction, whatever you have going in has got to be the current that goes out of the junction. Similarly, any current that goes out of a battery has got to be the current into the battery. So let's just take a really simple example. And let's say we have an ammeter that we put right here next to a battery and a resistor, right? We need a resistor to make this a good circuit, but it's got all the components that it needs. If you measure the current through the battery, let's say it had 2 amps. You know that the current that goes back into the battery, if you put another ammeter down here, there's got to also be 2 amps. So whatever that current is leaving has got to be the current that goes back into it. Now, if you were to put ammeters over here and measure the current through those resistors, that might be different. Like maybe you would have 2 amps coming into this and then they split, right? You could have 1 amp going down there, 1 amp going down there. You'd still have 2 amps into the junction, therefore 2 amps has to go out of it. Now they might not split evenly. Let's say, for example, you had 2 amps into a junction like this. And I'm just going to show the junction, I'm not going to show the battery here. And some of it goes down here, there's a resistor, and there's another resistor here. And you have 1.5 amps that goes that way. According to conservation of current, aka conservation of charge really, if you've got 2 amps coming into here, another like 2 coulombs per second coming into there, then you have to have 2 leaving. So if 2 go this way, you come to the junction, 1.5 goes this way, that must mean that there's another ½ amp down there. Other consequences of this is if we start looking at resistance, for example, applying Ohm's law, voltage is equal to current times resistance, we would find that these resistors have a different resistance, and you could even figure out potentially what that was. But the important thing to think now is, hey, if we've got conservation 2 amps in, you got to have 2 amps out. If you have 0.5 still coming through here, that means you've got to still have 1.5 there. They come together at this junction, so that means that out of this junction, you've got to have a total of 1.5 plus 0.5 or 2 amps out. So whatever you have in, you have going out as well. Obviously, something like this needs to be connected to a battery to have it, but you'll often see these kind of diagrams drawn independent of batteries. This is often called Kirchhoff's laws, by the way, and there's different ways to draw it, but just remember, what goes in must come out. It's pretty similar to water, right? You pour 2 gallons of water, and you might split it along a path. When the path comes together, you still got to have 2 gallons of water. So let's take something a little more complicated, like I have 4 paths right now. And so let's say that this has 2 amps going this way, and this has a ½ amp going this way, and this has 3 amps going that way. And you want to know an ammeter over here, what it's going to read. Well, let's think about this. You've got 2 amps in plus another 2 amps in. So a total in is going to equal a current of, and by the way, since we use the letter I for current, I'm just going to write that out as I sub in. Current going in is going to equal 5 amps. So that means you have to have 5 amps also going out. You got a ½ amp going there, so that 5 in equals current out. And that's going to equal, let's see, 0.5 amps plus some question mark that the ammeter is reading. So that means that if you've got 5 total, there's a ½ coming here, then this has got to be 5 minus a ½ or 4.5 amps. That's basically it. I mean, that's conservation of current in a nutshell. You'll see slightly more confusing questions related to this, but it almost always boils down to the same thing, like what goes in must come out, and you just need to make sure you're not confused by the diagrams. I can make simple changes to this as one more example. This will be quick. In has got to be equal to out. So let's say I have the same thing. I have 4 wires connected, but I changed the directions of them. So the first one's going to the right, the second one is going to the right, the third one is now going to the left. So current in is 2.5 amps, right? Current out is 3 amps. And this whole thing has to balance. In needs to equal out, so you know that you need to have another ½ amp going in, which means your ammeter is going to read another ½ amp this way. So in reality, you've got 2.5 amps plus a ½ amp, or 3 amps total, going in. And so then you have 3 amps going out. In equals out. I think that does it for this video. Thank you very much for watching.